Assalamualaikum warahmatullahi wabarakatuh and hello everyone. In this video, we're going to learn the second topic in SK015 chemistry called atomic structure, specifically subtopic number 1, Bohr's atomic model. As for this subtopic, we're going to first be introduced to the postulates of this model. There are 4 altogether. Then, to understand energy difference mentioned in the 4th postulate, we need to know what is meant by the ground state and also excited states, as well as a type of electromagnetic spectrum. Bohr's atomic model is made based on hydrogen atoms, so we will also be learning the 5 hydrogen emission series, Lyman, Balmer, Paschen, Brackett, and P-Fund, using the knowledge on ground and excited state, and also the Rydberg equations. Energy level can be up to infinity, therefore, we need to consider the energy required for complete removal of electrons at infinite distance. And lastly, as this model managed to cater only for one electron atom, there are some limitations arises due to dual nature of the electrons. This graphic shows the development of atomic model from time to time, but here in Matriculation syllabus, we are only interested in determining the movement of electrons within an orbit and between orbits. Therefore, we're going to take a deep dive into Niels Bohr invention. Niels Bohr is one of the physicists that deals with the extended ideas of energy quantizations to electromagnetic spectrum, just like Planck and Einstein. Before we talk more about this model, you need to first know the 2 important variables when dealing with light. There are frequency, denoted by nu symbol, and it represents number of waves per second. So if you could see from here, we have a number of waves within a second. While the other variable is wavelength, denoted by lambda symbol, is a distance between 2 identical points. So we have these 2 identical points on successive waves. When these 2 variables combined, their relationship determines speed of light. C is equal to nu times lambda. Bohr's model of hydrogen atom can be explained by using 4 postulates. First, he said that electrons move around the nucleus but only in prescribed orbits where the distance is fixed. Next, he emphasized that the potential energy of electrons of hydrogen atom at certain energy level is quantized. This means an electrons can only inhabit certain energy level at a time and they have specific energy. The quantizations of energy can be illustrated by using this formula, where RH is the Rydberg constant with the value of 2.18 10 to the power of negative 18 joule, and N is the energy level. From this example, we could see both energy of electrons at energy level 1 and energy level 4 has different value. And as the electron approaches the nucleus, where we could see from this E1, the energy increases compared to E4. In relation to the second postulates, Bohr suggests that there won't be any change in energy of electrons as long as the electrons are moving within an orbit in the third postulate. And electrons will transition from one energy level to another when a photon of a very specific energy is either absorbed or emitted by the electrons. The energy of the photon will correspond to the difference between 2 energy levels. So, if the electrons in hydrogen atom goes from n equal to 1 to n equal to 2, a photon will be absorbed. That is equivalent to that specific energy gap. If the electrons in hydrogen atom goes from n equal to 3 to n equal to 2, a photon will be emitted and has different energy gap associated with it. Basically, energy of a photon will rely on the equations we have discussed in the second postulate earlier. But when an electron transitions from one energy level to another, we can modify these equations to include the change in energy level delta E. So please take note that N1 in here is where the electron starts or initial energy level, while N2 is where the electrons end or the final energy level. Since transitions of electrons can happen either way, they can move from lower to high level known as absorptions and they gives delta E positive, and higher to lower level known as emissions or radiations, they give negative delta E value. So it is not necessary for the initial energy level to be lower than that of the final energy level. Let's say we take this example where E2 is the n equal to 2 and E1 is the n equal to 1, we're going to substitute the second postulate equations we have discussed into these equations. So we could see in here we have negative RH 1 over n2 to the power of 2 minus negative RH 1 over n1 to the power of 2 as suggested by this E2 minus E1. But then we could see in here we have negative and negative, means we're going to got positive, and then we're going to substitute in here. So if we want to keep this positive at the front, then we're going to swap this place of n1 at the back to the front like this, and lastly we can factorize it like this to become RH in the big bracket 1 over n1 squared minus 1 over n2 squared. So we can simply memorize this formula of delta E. When we say energy released or absorbed, it really have the same meaning as energy difference between energy level. So we're going to use these equations derived from earlier. We have delta E equal to RH. So your RH is the Rydberg constant, and then 1 over n1 squared minus 1 over n2 squared, where n1 is the initial energy level and n2 is the final energy level. You really need to include this in your equations. The energy emitted or absorbed is in the form of photon, thus it has specific energy and also wavelength. So by using the first equations in here, you can also predict the frequency and wavelength of a photon associated with any possible transitions of hydrogen atoms. So we could say from delta E, we can find the nu, which is the frequency, and from the nu, we can find the lambda, which is the wavelength. So you really need to know the constants used in here. We have C is the speed of light, 310 to the power of 8 meter per second, while H is the Planck constant, 6.6256 10 to the power of negative 34 joule second. So this constant will be given in the table of constants. Since transitions of electron must happen between allowed energy levels, apart from knowing initial and final energy level, you also need to know the ground state and excited state terms. An energy level is considered ground state when they are at the lowest energy states, usually n is equal to 1. But it is not always 1 because we're going to learn about hydrogen emission series later on, where you will see the ground state vary. Ground state is the most stable because the electrons are the closest to the nucleus. Excited state is obviously has higher energy than that of the ground states. If the ground state is 1, then the excited state must be 2, 3, 4, and etc. For an electron to reach this state, it must first absorb an amount of energy. Since it is located higher up and further from the nucleus, hence its stability decreases. To find the energy of electrons at both ground state and excited state, we can use the energy at individual energy level, which is negative RH 1 over n squared. Let's try this one example. Given 1 mole of electrons drops from the 4th energy level to the 3rd energy level. From the statement, we could say the transitions of electron happens from n initial of 4 to n final of 3. But as for A, the questions asks for energy of electrons at the 4th energy level, means it asks for energy at n equal to 4 only. For individual energy level, we're going to use the equations from the second postulate, negative RH 1 over n squared. Substitute n is equal to 4, and the Rydberg constant is 2.18 10 to the power of negative 18 joule. You will get this answer of negative 1.36 10 to the power of negative 9 joule. Please remember, for every energy of electrons at particular orbit, the value going to be negative. Question B asks you to calculate energy of photon emitted. When it says emitted, means transitions happen between two energy levels. Since we know already the n initial and n final, we are going to use this formula of delta E is equal to RH 1 over n1 squared minus 1 over n2 squared, where our n1 going to be the initial energy level, n2 going to be the final energy level. Once we substitute all the value into the formula, then we're going to get delta E of negative 1.06 10 to the power of negative 9 joule. Please remember that the unit for energy is only joule. Lastly, C, it asks for frequency of photon. Since the energy emitted in the form of photon, therefore we could use another formula of delta that contain frequency, which is h mu. So once we rearrange this formula, we're going to get delta E over h, which is the Planck constant. We'll substitute all the value and we're going to cancel out the joule unit, left only with per second with the value of 1.6 10 to the power of 14. So the unit of frequency, it could be in per second or in hertz. Transitions of electrons from higher energy level to lower energy level will form radiations. The electromagnetic radiations consist of radiations of all sorts of wavelength, though they all travel at the speed of light, but their frequency and wavelength vary. The radiations range is made with respect to wavelength or frequency, resulting two types of spectrum, continuous and line spectrum. Continuous spectrum is a spectrum of radiations that contains of all wavelength. There's no definite line that separates these colors. For example, we have rainbows. You can barely see the line that separates each color present. In contrast to continuous spectrum, line spectrum is a spectrum of radiations that consists of discrete lines of specific wavelength. An example of line spectrum is hydrogen spectrum. This hydrogen spectrum can be divided into two. One is emission spectrums, where transitions of electrons happen from higher energy level to lower energy level, and absorption spectrum is where transitions of electrons happen from lower energy level to higher energy level. All the calculations of energy we have discussed previously belongs to hydrogen atom. As we said these energies are unique to hydrogens, every element will also have its own emission spectrum because every element has a unique nucleus, therefore differently spaced energy level, as you could see from this line spectrum for Hg and Xr. Bohr's model explained the spectral lines of hydrogen atomic emission spectrums. Those discrete lines formed reflects that energy is quantized. Now we're going to discuss how hydrogen emission spectrum is formed. First, energy is supplied to the hydrogen gas in the discharge tube where the electrons are located. Then, electrons of the hydrogen atoms at ground state will absorb the energy and excite to a higher energy level. For this example, we're going to use ground state of 1 and excited state of 4. At the excited states, electrons are unstable. They will eventually fall to a lower level and produce radiations in the form of photons of a specific wavelength. Lastly, lights with a specific wavelength fall on the photograph plate and lines are recorded, so this is what we call line spectrum. How can this line be recorded? By transferring this small part of orbit here and relate it to the equations of delta E equal to hc over lambda, then we're going to get our reading on the line spectrum. It is important for you to know the ground state and excited state of each emission series in order to calculate all sorts of information needed, such as energy of photon or frequency or wavelength. We have 5 hydrogen emission series to learn. Lyman series with ground state of 1 and excited state of 2 onwards happen to contain transitions that emit photon to fall in the ultraviolet spectrum. Bohr'S series with ground state of 2 and excited state of 3 onwards happen to contain transitions that emit photons to fall in the visible spectrum. Paschen series with ground state of 3 and excited state of 4 onwards, bracket series of ground state 4 and excited state of 5 onwards, P1 series with ground state of 5 and excited state of 6 onwards are all results photon that transitions emits to fall in the infrared spectrum. This is an example of how transitions of electrons on an energy level diagram will look like for a number of series. We group the transitions according to the energy level they land on. All the ones that end on n is equal to 1 are called the Lyman series. The ones that land on n equal to 2 are the Bohr'S series, and so forth. We have Paschen n equal to 3, bracket n equal to 4, and the other one P1 n is equal to 5. So the aim is to have exactly the same ground state. Notice that energy level gaps decreases as n increases. So the answer to this relationship can be found in the equations of delta E is equal to hc over lambda. When n is equal to infinity, it is actually a finite distance from the nucleus. If electron goes beyond that, it is considered to have been ejected from the atom, known as ionization's energy we'll cover afterwards. How can line spectrum be formed from an energy level diagram? There are 2 components you needed here. One is energy level diagram, another one is line spectrum. If the question asks you to show the transitions of electrons or draw energy level diagram, you only need this part. But if the questions ask for spectral lines or line produced, you will need to have the other part. But sometimes they can ask for both, depend on the question. To draw energy level diagram, you will need to start with this y-axis of energy and horizontal lines of energy level separated by different gaps. From the electron transitions given, we could see all the electrons landed on the same energy level, which is 2. So based on the 5 hydrogen emission series we have learned, this is probably Bohr'S series. So we're going to relate the formations of line spectrum to this formula of delta E is equal to Hc over lambda, where it suggests when delta E decreases, this delta E can be found in here 3 to 2, 4 to 2, 5 to 2, and so forth. Hence, the wavelength formed on this line spectrum increases. The first electron transitions in this series takes place between n is equal to 3 to n is equal to 2 to form the first line on the far left with wavelength of 656.3 nanometer. Not necessarily left, sometimes it can also be on the right, depend on which side of energy level diagram does the transitions located. Second line formed from the second transitions, n is equal to 4 to n is equal to 2, give wavelength of 486.1 nanometer, followed by the third line with wavelength 434.1 nanometer formed from the third transitions n equal to 5 to n equal to 2. And lastly, the fourth line formed has the smallest wavelength, as you can see here, 410.1 nanometer, as its energy gap is the biggest from n equal to 6 to n equal to 2. Don't forget to include the trend of this line spectrum like this. To the right, delta E increases, wavelength decreases. Bohr'S series happen to contain transitions that generate photons of visible light. These are the ones found on the hydrogen emission spectrums. This line corresponds to the electron transitions that ends at n equal to 2 and the resulting photon that transitions emit, which just happen to fall in the visible spectrum. So, if the question states anything about colored lines like these, red color, green color, blue color, and so forth, without mentioning the name of series or the ground state, we know for sure that they belong to the Bohr'S series. For this example, let's first decide the trend in line spectrum. We could see the gaps become smaller from line A to line E. These gaps tells you about their wavelength. So we know for sure wavelength decreases as we move from right to left, means the delta E increase. So smallest delta E results in the greatest wavelength. As you can see in here, we have A has the greatest wavelength, give rise to the first line comes from the first transitions in partial series with ground state of n equal to 3. For question A, it asks for the line in the partial series correspond to the longest wavelength of photon. So we could say that this line A got the longest wavelength. As for B, you need to describe the transitions that give rise to the line D. So let's start with this first line A, B gonna be the second line, C gonna be the third line, and D gonna be the fourth line. So the fourth line is produced from the electrons movement from n equal to 7 to n equal to 3. Apart from energy difference and energy of photon equations we have learned earlier, you could also use these Rydberg equations to calculate wavelength straight away from the excited state and ground states given. So the equations will look like this, where you have this 1 over lambda equal to RH 1 over n1 squared minus 1 over n2 squared. So these equations look pretty similar to the delta E equations in previous slides, but then the exceptions applied here is a bit different from the one we have used in delta E. Here we have this lambda. Lambda we know is just distance between successive waves. So this distance must have positive value. So that's why the lambda that you're going to get must be in positive value which is greater than 0. Therefore, the N1 and N2 applied in here, the N1 is not necessarily initial, but the N1 must be less than that of N2. So as for the RH constant, the Rydberg constants, we're going to use different Rydberg constant, which is 1.097 10 to the power of 7 per meter. In previous equations, we used Rydberg constants in joule. Now we're going to use in per meter because we are interested in this wavelength. Rydberg equations can be derived from these two equations. So we're going to substitute these equations, and then by keeping only 1 over lambda on one side and everything else is bring to the other side, we will end up with this formula. So please note that this RH in here, we're going to use the amount in per meter. How do we get this per meter? It is basically this RH divided by HC. Then we're going to keep it as RH with different value. For this example, you need to calculate the wavelength of the third line of the Bohr'S series. So given information in the questions, Bohr'S series means you already know the ground state going to be n equal to 2. And this third line is from the third transitions where n is equal to 5. So you should first state the third line in Bohr'S series is from n equal to 5 to n is equal to 2. Don't forget to indicate your N1 with the smallest value and N2 with the bigger value, because the exceptions apply in Rydberg equations. N1 must be less than that N2. So you now have N1, N2 and also your RH. Then you can simply substitute into your formula. And then lastly, you will get lambda equal to 4.341 10 to the power of negative 6 meter. Sometimes the questions can ask you to change it to nanometer, but you really need to change it to nanometer if and only the questions ask you to do so. If not, you can keep it as it is in meter. Make sure to have the unit. No unit, no marks. What will happen to the energy of electrons if it reaches n equal to infinity? If the electron goes beyond infinite distance, the energy is approaching zero because it is considered to have been ejected completely from the atom, hence no longer attracted to the nucleus. Once this happened, the atom is said to be ionized. For energy difference between n is equal to 1 and n is equal to infinity, it is called ionization energy. Ionization energy is the minimum energy needed for the complete removal of 1 mole of electrons from 1 mole of gaseous atoms or ions. So please take note in here, the unit for ionization energy is no longer the same as in the delta E we have learned just now. They are going to have per mole after the kilojoule, means we need to consider this into our calculations. So given to you example of this reaction, hydrogen gas atom to form hydrogen plus in gases and also electron. So this electron will be removed completely from the atom. So for this energy to be calculated, we need to consider N1 is equal to 1 and N2 is the infinity. Then only we can proceed to the calculations of delta E. But this is not the end of this ionization energy calculation since we got this per mole. For the calculations of delta E, we're going to consider this energy level diagram. So this is basically the energy level provided. Then we're gonna have this E1 equal to negative 2.18 10 power of negative 18 divided by 1 square. And then for E infinity, as it will be completely removed from the atom, they're gonna have a value of 0. So the delta E will eventually gives you exactly the same value as in the E1. You need to continue on your calculations by relating the 1 mole of H atom contains 6.02 10 to the power of 23 hydrogen atoms. So this value comes from the Avogadro constant. So for removal of 1 mole of electrons from 1 mole of hydrogen atom, we're going to relate it to this Avogadro constant. And since this atom can be cancelled with this atom, hence we are left with only 1.312 10 to the power of 6 joule per mole. If we want to change it to kilojoule per mole, we need to apply the prefix of 10 power of 3 to get the kilo, And lastly, we're going to have 1312 kilojoule per mole as our final answer for ionization's energy. Bohr's was successful in introducing the idea of quantum and also explaining the lines of hydrogen spectrum. But this idea only caters for one hydrogen atom only, so there are limitations arises due to the weaknesses in its atomic model. So the first weakness gonna be it explains only the hydrogen spectrum or spectrum of ions that contain one electron, such as He+ or Li2+, means we cannot use for any other element. Other than that, it could not predict line spectra for other atoms. And lastly, he proposed that electrons could only orbit at specific fixed distance from nucleus. However, electrons is so small that they cannot travel in a fixed orbit. The limitations of Bohr's could be overcome by considering the dual nature of electrons proposed by de Broglie. He suggests that particles such as electrons can have wave properties. That is, perhaps matter is wave-like as well as particle-like. This dual nature of electrons can be demonstrated by combining the equations for mass energy equivalence, E is equal to mc squared, with that of energy of photon, E is equal to hc over lambda. So we're going to combine these two and set it aside to have only lambda on the left hand side, and the rest going to be h over mc. Unfortunately, using the equations alone still cannot determine where exactly the locations of electrons in an atom due to uncertainty arises, where fixed path of electrons cannot be assigned, and they should have considered region of space in determining the locations of electrons. If electrons are wave-like, how can the positions of an electrons in an atom be specified? So Heisenberg answered to these questions by stating it is impossible to know simultaneously the exact locations and momentum of a particle. Therefore, he proposed this uncertainty principle of delta x, where this delta x is the uncertainty in positions, m delta u belongs to the uncertainty in momentum, is greater than or equal to h in here is the Planck constant divided by 4 pi. That's all for subtopic 2.1. You may now proceed to the 2.1 tutorial starting from NFTF week 5 hour 1 until FTF week 5 hour 3. Thank you for your attention. Goodbye.